Okay, hi guys. We are on day 1 of our distance learning instruction, and we're going to continue along with our electric current packet. So if you have your notes, take them out. We're going to start on page 17 where we left off, and I want you to start thinking about parallel circuits and what happens when we're in a parallel circuit and the number of resistors in parallel increases. Okay, so we're going to answer letters A through F. I want you to take a moment, maybe pause the video, and think about each question, and then we'll go over them together. So if you recall, parallel circuits, the total resistance, that actually adds inversely. So if we were adding up resistors in parallel, we would do 1 over R1 plus 1 over R2 plus 1 over R3. And then we would take the inverse of the sum to get the total or the equivalent resistance. So as the number of resistors in parallel increases, the total resistance actually decreases, which is kind of counterintuitive if you think about it. So for REQ, as we increase resistors, it decreases the overall resistance. Okay, think about what happens to the total voltage. That's the voltage supplied by the battery as the number of resistors increases. You should really think, well, if my total voltage is supplied by the battery, it wouldn't matter how many resistors are connected. So that should remain the same. So that wouldn't change at all. Okay, but current, we do have to think about that. Total current is what's supplied at the battery. So if you think about our current equation, which would be total current equals the total voltage coming out of the battery divided by the total resistance, which is REQ. This remained the same, the total voltage. REQ actually decreased. So if we are thinking about current, the numerator remains the same, the denominator gets smaller. Our total current provided to the circuit actually increases as we add more resistors in parallel. And this is actually why parallel circuits are superior. It doesn't matter how many circuits or how many junction points you have, how many resistors you have, the circuit will always provide more current to serve those branches. Okay, let's think about the current across each resistor. All right, if you think about those branches in parallel, we have those junction points. All right, and I told you that little thing about parallel circuits, parallel PVC, voltage remains constant. So if we think about that in parallel, the voltage over each resistor remains the same, and the actual resistance of each resistor remains the same. So if you did a little calculation for current, knowing that the voltage across the resistor remains the same, the resistance of the resistor remains the same, the current supplied to each resistor actually remains the same as well. All right, the last two, the power to each resistor. All right, what would happen? Well, we would think about what I just said in the last example. If we look at the individual resistor, voltage remains the same, resistance remains the same. So if we think about maybe this equation for power, power is V squared over R, both those things remain the same. So power actually also remains the same. Okay, and the last one, F, if we think about brightness, if you recall, brightness is proportional to the power supplied to the bulb. So along the same lines of thinking, if we have the same voltage, resistance, current, then our power is the same, therefore our brightness remains the same. All right, let's just finish up this page of notes and looking at what we have here. We have a 5 ohm, a 10 ohm, and a 15 ohm resistor, and they're connected in parallel. And in part A, it says, which one has the most current passing through it? All right, so recall again, parallel circuit. Parallel circuits, PVC, voltage remains constant. So if we look at any of those resistors, the voltage will be constant. So if I were to do an individual calculation for current, that would be V over R. Voltage remains the same. As resistance goes up, the current would actually go down. All right, so the one with the least current has the greatest resistance, and the one with the greatest current has the least resistance. So the one with the most current would be the 5 ohm resistor. Okay, to remember again, we could do it the other way. If we have resistance decreasing in the denominator, that would actually make I go up. All right, now in part B, it says, which one has the largest potential difference across it? This would be the voltage reading across the resistor. Okay, so thinking about that, we're in a parallel circuit. Parallel circuit, voltage is constant. So they would actually all have the same potential difference across each resistor. All right, the next question, we have the same resistors, a 5 ohm, a 10 ohm, and a 15 ohm resistor, but this time they're connected in series. What do we know about series? You should all remember. You all should remember, because I made you say it a few times. Series is sick. Series current is constant. And in part A, it asks us which one has the most current. Well, if you remember, series is sick. Current means the same. We know that it doesn't matter which resistor we're looking at. We only have that one-way path for the charges to flow. So you would get the same current reading anywhere you put an ammeter in the circuit. All right, but part B, it says which one has the largest potential difference across it? That's voltage, yet again. Since we know we have the same current everywhere, and I think about, well, I have to use Ohm's law to calculate potential distance, difference. I remains the same. As R goes up, V goes up, we'd have a direct relationship. So the 15 ohm would have the greatest potential difference across it in series because it has the same current and has a direct relationship with resistance. Okay, so now we're going to learn about Kirchhoff's junction rule. It's Kirchhoff's #1 rule. And we already kind of covered this when we looked at parallel circuits, but we're going to look at it again. And basically, this is based off of the conservation of charge. However much charge is coming into a junction point, that's where 2 wires meet, has to leave that junction point. The charge can't be created nor destroyed, so whatever comes in has to go out. So it's a very simple process, and you basically look at a position where the 2 wires meet, such as that point in letter A, and we see we have the charges or the current going in. Let me change that. Boop. So we have current in is equal to the current going out. And the current going in, we have 5 amps going into that point. Going out, we're showing only 2 amps going out. So if you look at X, we could pretty much make a determination that X has to be on the outside, and you do some basic math here, and we've realized that we have to have 3 amps leaving this point in the circuit. Okay, so why don't you pause the video and try the next couple questions, and I will go along and do the answers as well. All right, so if we look at B, B is a little bit more advanced. We have 2 junctions and we have 2 unknowns at this point. But you just take each junction at a time and apply Kirchhoff's #1 rule, the junction rule. What goes in must come out. So going into this junction point, we have 10 amps going in. So we have nothing coming out. So that must mean that X1 over here has to equal 10 amps. Then we look at our next junction point. This 10 amps just continues along. So then we have 10 amps going into this junction, 3 amps going into this junction. So X2 has to be 13 amps going out. All right, if you look at letter C, we have quite a few wires all connected at this central point. And we might need to make a little list over here so we could keep track. Current going in has to equal current going out. So looking at the arrows pointing into the junction, entering the junction point, I have a 4 amp and a 6 amp, and then it looks like everything else is leaving. So we have 1 amp, 5 amps, 3 amps, and then X amps. So we have 10 amps going in, we have 9 plus X going out, so X has to equal 1 amp, okay? The in and the out has to be balanced. All right, now looking at letter D, I think this one requires like some math, so you might need a calculator for this one. And it says find the current in each resistor. We have 12 amps coming in, so this 12 amp is going to break up based on how much resistance is at each point. You could go as far as like calculating the voltage that might be there after finding an equivalent resistance. But I believe we could just do this through some sort of ratio. Okay, so grab your calculators and we'll give this a try. Okay guys, so I did a little work ahead so we wouldn't spend all the time watching me and waiting for me to use my calculator. So I did a quick REQ calculation where this is a parallel circuit. So I had to do the inverse of the sum of all of the resistors. And I knew the total current coming into that portion was 12 amps. So I calculated out that the voltage serving this branch was 8.76 volts. And using the known voltage, because parallel voltage is constant, I'm going to do an individual current calculation for each one of those resistors using I equals V over R, keeping in mind that R1 is equal to R4. Those are 2 ohms. And you could already kind of see how this is going to work out. If R increases where voltage remains the same, current's going to go down. So we're going to have the largest current through the smallest resistor, and as the resistance goes up, the current's going to go down. So we should have the largest through R2, followed by, we're going to have the largest through the 2 ohm resistor, which is R1 and R4, followed by R2, followed by R3. Okay, so I just did Ohm's law solving for current 3 different times, and the answers are on this page. So let's say we have this constant, parallel voltage is constant voltage, and then we have all of my resistances, and then we could see this is I1, 4.38, just like we suspected, followed by I2, 2.19, and then I3, 1.095 amps. Okay, so that should do it for Kirchhoff's junction rule. We use this pretty much anytime we have a parallel circuit, and we can also use this for when we have combination circuits, which is coming up next, and probably the most challenging part of this unit. It takes a lot of thinking. Okay, so I'm signing off now, trying to do another video. Okay guys, now we're going to dive into combination circuits. And you're going to notice in every combination circuit, we're going to have a little bit that looks like and acts like a series circuit. And then we have a little bit of the circuit that is a parallel circuit. And you have to do your best to simplify the circuit, solve for the same things we've always been solving for, the voltage over every resistor, the current over every resistor, the equivalent resistance. And you kind of have to work your way out of the circuit by combining the resistances, making the circuit simpler and simpler, and then solve for what you can. I'm going to teach you like my methodology. Hopefully it'll come across in this video, and then you could try a bunch of problems after that. So combination circuits, you always have to ask yourself, does the current split? If the answer is yes, you're dealing with the part of the circuit that is acting like a parallel branching circuit, because we have splitting current with a parallel circuit. If the answer is no, then you're dealing with a series circuit. And once you decide whether the portion of the circuit is parallel or series, then you apply the rules that go along with series circuit or parallel circuit. All right. And anytime you're dealing with a combination circuit, I say start with the most, like the most complex part of the circuit and try to simplify it and work your way out. So if I'm looking at this circuit, this part to me is the most like complex part of the circuit. Everything else is just a regular series circuit. So a good idea would be to like locate your battery. Here we have a cell. It's just, same kind of thing where it's our source of potential. But you can see that the current comes out of the positive side of the battery because we follow conventional current, and it hits that junction point. So up until that point, we still have the total current that's coming from our battery, and then it's going to split 3 ways. It's going to go over those 3 resistors. And so this portion would be a parallel part of our combination circuit, those 3 resistors. And those currents go over each resistor, and then they would join back up at this junction point. And we would have our total current again, and that would go over this 12 ohm resistor. So the 12 ohm is actually a series resistor, and it's in series with our battery. I know it's in series because the current doesn't split between it. Okay, so I would always trace out the current before you begin a problem and kind of look at what's happening there. Okay, all right, so what did I mean by you make the circuit simpler? So you look at the resistors, you find like the most complex part of your circuit, and you try to combine them. So for us in this one, it would be these 3 that are in parallel. Now this isn't that hard because we've done parallel circuits before, but pretend you could take those and you can take those 3 and just smush them together and make one resistor. So instead of having 3 separate ones, I could redraw my circuit as a simpler circuit. I would still have my 12 over by itself, but I took those 3 and I smushed them together and I made one equivalent resistance. So there's my 12. This is still 30 volts. And in order to figure out the equivalent resistance, I actually have to do a calculation. Since they're in parallel, I need to add up the 3 resistors inversely and take the inverse of their sum. So if you add them all together, you get an equivalent resistance for just the parallel section, and that comes out to 3 ohms. So if you squish them all together, you get an equivalent resistance of 3 ohms. Now, if you look at the 2 resistances we have a 12 ohm and we have a 3 ohm. So if we added those together, because they're in series with one another, you would get an equivalent 15 ohm resistance. And you might be asking, well, how do I know that these are in series? Always follow the current. Since I squished the 3 down that were in parallel and made an equivalent resistance of 3 ohms, now the total current passes through that equivalent 3 ohms, and then the total current passes through that 12 ohm. So these 2 are in series with one another, and I could add them directly. And that's how I got a 15 ohm equivalent resistance for the circuit. And our cell is still 30 volts. So I could take this end picture and actually figure out the total current that's coming from my battery by doing V total divided by REQ for the circuit. So V total was 30 volts, my REQ was 15 ohms, so I have 2 amps that serves my circuit. So I have 2 amps over this 15 ohm resistor, and then when I go up a level, I have 2 amps over this 12 ohm resistor and 2 amps going over that equivalent 3 ohm resistance. Okay, this is an important step because a part of combination circuits is you have to find out the voltage or the potential drop over each resistor. So I could figure out how much voltage is serving this 12 ohm resistor by doing V equals IR. Okay, so over the 12, I would have 2 amps, resistance of 12 ohms. So that would mean I would have 24 volts serving that 12 ohm resistor. And if we do a little subtraction from the battery, I'll have the voltage going to the 12 ohm resistor plus the voltage going over that, equivalent 3 ohm resistor. I'm going to have 30 volts minus 24 volts. That's going to leave me 6 volts going over this portion of the circuit. Okay, and then this brings us back to our original picture. I know I have 24 volts over this resistor, and this is a parallel branch. Okay, so if I go up a level now, I could apply the concept of parallel voltage is constant. So that means I'm going to have 6 volts here, 6 volts here, and 6 volts here. And I know all of the resistances. So I could actually find the current over each resistor of that parallel branch. And I guess we'll do that now. So I'm running out of space here. But if I look at, let's say, the 18, we're going to do V over R. Now the voltage serving that branch is 6 volts. Okay, 6 volts over 18 ohms, that's 1/3 amp. Okay, and we're going to do the same thing for the 9. So I'll move up here. I for 9 is going to be V over R. So that's going to be 6 volts over 9 ohms. Okay, so that's going to be 2/3 over there. Now we're going to do the current over the 6 ohm resistor. So that's V over R again. That's going to be 6 volts divided by 6 ohms. 6 divided by 6, we have 1 amp. So now apply the concept you learned about either Kirchhoff or going back to parallel branching circuits. We had 2 amps going into that junction point. We have 1/3 amp going to the top branch. We have 2/3 going to the middle branch. We have 1 amp going to the bottom branch. 1/3 plus 2/3 plus 1 equals 2. And so that applies Kirchhoff's rule that the current going in must equal the current going out. And it also works for our parallel circuit where the currents have to add up to whatever branched off. So this is what you have to do in each case. These problems are a little long, and they're especially long when you're trying to make videos of them. But use the knowledge you have of series and parallel. Always start with the most complex part of the circuit, break it down, ask yourself, does the current split? If it splits, it's parallel. If it doesn't split between the resistors, then it's series. Okay? I'll try the next couple to do more answer keys, and I think you should try to do them before me, and then we could go over them together. Okay?